Today we have Jeremy Latriano from 475 High Building Performance Supply, and he's going to be talking to you today about high performance roof daylighting. Jeremy Latriano, off you go.
Awesome. Thank you, Mike. Appreciate it. Thanks for the invite today. Good afternoon, AI East Bay. Thanks for taking the time out of your busy schedules to join me for this presentation this afternoon. As Mike so generously mentioned, my name is Jeremy, and I am a product consultant at 475 High Performance Building Supply. I specialize in our skylight products, and I'm excited to talk to you today a little bit about those products and a little bit about how we can incorporate roof daylighting, i.e. skylights, into high performance building enclosures. I've been with 475 for about 7.5 years. And for pretty much the entirety of my time at the company, and even a couple of years before that, we were operating our headquarters out of what essentially amounted to an outfitted garage in the Gowanus neighborhood of Brooklyn. This building, which served as our company headquarters for almost 10 years, was really the definition of uncomfortable and energy inefficient. The building enclosure was uninsulated and very leaky, both in terms of air and sometimes water. It had really no windows, and so we received very little natural light. We made an admirable effort as a company to improve the performance of this enclosure in order to boost its comfort and energy efficiency. But despite our efforts, we were never able to completely eliminate our reliance on a large gas burning heater, which certainly did not aid the indoor air quality for the space. Fast forward to the present, and our company now operates out of a retrofitted masonry building, not far from the old office geographically, but worlds apart in terms of performance. This new building encapsulates the characteristics, components, and methods that our company advocates for and features many of the high performance products that our company supplies. These products include the Proclima air sealing system, continuous and balanced energy recovery ventilation through the Brink ERB system, and triple glazed thermally broken skylights from German manufacturer Lamlux. These products, along with careful planning and detailing, have allowed us to achieve Pass-Fail certification for this renovated space, which means that our building uses extremely little energy for heating and cooling, and thanks to the solar PV on our roof, is able to easily achieve net zero energy performance. For more information on the products that our company supplies, I highly recommend visiting our website at 475.supply, where you can see a variety of product pages and knowledge resources. Specifically, I'd recommend checking out our Smart Enclosure, which is a series of free ebooks and CAD details you can download off of our website, which feature our best practice recommendations for high performance construction assemblies in a variety of different construction typologies. So normally at this portion of the presentation, I would launch into a few slides talking about our company history and talking about some of the products that we supply, specifically the skylight products, which I specialize in and which I'll elaborate more on today. But I thought it might be fun, since we are in this new office space, to kind of show off some of these products as they are applied within this renovated building. So I'm going to try something now. I'm going to attempt to change my device from my computer to my cell phone. Bear with me a second, and then I'm just going to take you on a quick walkthrough of our building. Okay. Hopefully you guys can hear me.
Yep, we can.
Perfect. You'll see my cell phone here, starting in the conference room here, walking out into the main office space. So I mentioned we work with a couple of different European manufacturers to supply skylights here in the US and Canada. The main product we've featured in our new office is Lamlux skylights, which are manufactured in Germany. You can see a large one featured here over our main working space. The PR60 is a knockdown system, or otherwise known as a mullion and transom system. So it's delivered to the job site as a kit of parts. This kit of parts includes triple layer insulated glazing, thermally broken aluminum profiles, and then insulated flashing connections to the existing structure. This kit of parts comes together on site to provide a thermally continuous and quite elegant skylight solution. In this case, you can see that we feature three glass fields, one of which is an operable ventilator flap, which also allows for fresh air to enter into the space. What you'll notice about this space is that on three of the four walls, we share a party wall with the neighboring structures. And so we weren't really able to utilize many windows to bring in natural light. So we relied heavily on these skylights to do so. The second product I just want to show you guys as part of this tour is the Lamlux Comfort Swing. Same manufacturer, Lamlux, out of Germany. This is a roof access skylight. So you can see we feature it over the top of our staircase. Similar to the PR60 and most of the Lamlux offerings, it is a thermally continuous solution. So it has triple layer insulated glazing and a thermally broken, continuously insulated frame. The skylight operates via two pneumatic pistons and a hinged edge, so we can open it mechanically to allow for roof access, a really nice feature to expand access to the outdoors, particularly in urban environments that might not otherwise be able to get that access. Close that for you guys. It's getting a little cold here in Brooklyn. As I pivot to the front of our building, you can see here the Lamilux FE Circular, a nice design option for projects that are looking to utilize a circular skylight. You can see this unit skylight comes pre-assembled with triple layer glazing and a thermally broken frame. It also features this insulated curb, which you can see in the white well beneath the skylight. That curb is delivered as part of the skylight assembly, and it allows you to easily install the skylight and detail your water, thermal, and air control to the surrounding structure. I'll talk a little bit more about that detailing in my presentation. Getting away from the skylights here for a second as we move into our mechanical room. So our company doesn't only deal with skylight products. We supply a variety of different solutions to help buildings reduce their energy usage for heating and cooling, and also to improve the comfort and efficiency of their spaces. This is the Brink Energy Recovery Ventilation System, which supplies air continuously to our office space in spaces such as the areas where we work and our conference room. It also constantly exhausts air from areas such as bathrooms and kitchens. And so we are able to achieve very high indoor air quality. And while this system is exhausting air, it's preserving some of the heat from that air in this box. And so that as air is being exhausted, we're preserving the heat from that exhaust air. And then when we supply air through these uninsulated ducts, we can see that the supply air then recovers some of that heat, thereby allowing us to ventilate constantly without having to worry about compromising our energy performance. Just want to take you guys downstairs quickly just to feature our truth window and some of the materials that are included in our enclosure. As I mentioned, this enclosure is continuously air sealed and insulated. So we have very low energy usage for heating and cooling, and we're able to quite easily get to net zero energy usage thanks to the PV on our roof. The optimization of the enclosure can be seen here in the truth window, which gives you a little bit of a peek behind our finishes. Here we show a laminated mineral wool product from Rockwool called Smart Rock. This product is one of the newest that we've launched in the US and Canada. It has a semi-rigid mineral wool insulation board with an interior air control and vapor variable membrane laminated to it. So that can be easily installed and then taped at the seams using this blue tape to check off two boxes, insulating and air sealing in one. This is the general principle of how we achieve such high performance via this air tightness, which is continuous via this membrane to the roof where it connects to our roofing membrane, and then also to the slab where it connects to our sub-slab poly. So I'll take you now back to the conference room, and I will switch my device back and we can launch into the AIA portion of the presentation. Just bear with me a moment here. Okay, and I'm back here. I'm going to share my screen with you guys again. Okay, all good there, Mike?
Looks great.
Awesome. Worked out better than I expected. Cool. So some of the products I highlighted are shown here. Our company is an e-commerce business, so our store is our website. So as I mentioned, for any more information on the products that we supply, you can visit that website. So to give a quick summary of those products, we have the air and vapor control system, which is supplied primarily from Proclima, the manufacturer of that Intello Plus membrane I showed you guys in the truth window, as well as a variety of other interior and exterior tapes and membranes, which can be used to achieve very high levels of air tightness and vapor control. We also supply a sub poly wrap for Stego, so we can help you seal all sides of your enclosure. We supply insulation through a German manufacturer, Jutex, who produces wood fiberboard insulation, a product that is rigid board exterior insulation in WRB and offers exceptionally low embodied carbon. We also supply, as I mentioned, the Brink Energy Recovery Ventilation System, which is a centralized ERV, and we can also do a decentralized through-wall ERV through German manufacturer Lunos. For the products that I'm here to talk primarily about today, and really more to talk about in terms of general principles, are our roof daylighting products, Lamilux, which we showed you guys around the office, and then also Facro, a Polish manufacturer of deck-mounted skylights specifically. Because I didn't get to show you guys those, I'll show you those, just describe them for you briefly. These skylights, while Lamilux is intended for low pitch and flat roof applications, the background skylights we supply can be used in pitched roof applications. These skylights feature a thermally broken timber frame and triple layer insulated glazing. They can be supplied as fixed or operable. We do have some stock options available here in the US. In addition, we can also do through Thacro walkable skylights, also triple glazed with thermally broken extruded profiles, up to about 4 foot by 4 foot in dimension. All right. So now that we have learned a little bit about our company, some of the products that we supply, I want to take us into the AIA portion of the presentation. So if you would like to receive credit for this presentation, which will take the remainder of our time, you can go ahead and take out your phone and scan this QR code on the screen, which will take you to a Google survey where you can fill out basic information about the presentation, provide our number and course number, which are listed here, today's date, and then also your AIA information, just so we can make sure that you get credited. So I'll
That
leave that up
one
for a
of
minute.
one of our members, Mick, has a question. Will there be a handout for this presentation?
I'm definitely happy, Mick, to follow up with some materials about our products. I don't have, I have flyers for those products, and I'm definitely happy to send you a PDF of this presentation if that would be interesting. So maybe we can connect then at the end. Take down your email and get that over to you.
He says yes, thanks.
Perfect. So I'll give you guys a minute here just to scan this QR. All right. And if there are no objections, I'm going to go ahead and launch into the presentation. So as I mentioned today, here to talk to you about high performance roof day lighting being skylights. We'll take a few minutes now just to define what our company means generally when we say high performance. It's a term that we throw around quite often. It's in our company name, but it's pretty general. I think we can agree in its description. So let's define this term and talk a little bit about what high performance means to our company. So I'm going to ask for some audience participation here. I know that you guys are on lunch, so feel free to keep your cameras off. But if you could entertain me and respond to some of my prompts here, I think that would make it a little bit more fun for everybody. So we'll start with this very simple question: what is high performance? And when I say high performance buildings, high performance building supply, what sort of building characteristics or qualities come to mind?
Insulation,
Insulation, certainly, yes, one that we explored a little bit on our office tour. High performance buildings, by our definition, are continuously insulated, and they minimize thermal bridging, which is conductive materials that might allow heat transfer to bypass our insulation layer. Insulation will eliminate cold spots at the interior. It'll minimize risk of condensation, and it'll also significantly reduce our heating and cooling demand.
waterproofing,
Waterproofing, absolutely, yes. We're going to talk today about building control layers, one of which, and the most important of which, is water control. Basically, if our buildings can't keep out water, they're not really doing their job, even at the most basic sense. When water control is not detailed effectively, we can have water leakage, we can have saturation, we can have building rot and molds, and overall, our building is not going to be durable and barely inhabitable. So yes, absolutely, water protection is critical to high performance.
You've got a couple people on chat too, so if you open the chat, you can see there's questions there. One Mick says tight envelope, and Yolanda says energy efficiency.
Both great answers. Thank you, Mick and Yolanda. Tight envelope, absolutely. Air sealing, particularly, is the most effective way we can reduce mechanical heating and cooling requirements, even more so than insulating. Air sealing also maximizes our comfort as we eliminate drafts, and it's going to improve the durability of our structure as controlling airflow limits vapor movement. And energy efficiency, yes, that is the big one as well. We talk about all these different characteristics, air control, insulation. One of the big things that we're trying to capitalize on is energy efficiency. And when we do achieve very high levels of air tightness and thermal protection, we're actually able to get to a point where mechanical heating and cooling loads are minimized, that they can be supplied electrically and offset using renewables. So also really good answers there. Some other things that we as a company consider as essential qualities of a high performance building. The first is comfort. These buildings, high performance buildings in general, are going to be exceptionally comfortable. This is because they embody some of the characteristics that you guys mentioned. They're continuously air sealed, so there's no air leakage, no draftiness, no temperature asymmetry. Similarly, because they're insulated, we don't have any cold spots or any cold surfaces. We'll talk a little bit about the effects that those can have on comfort. High performance buildings can be very healthy. This is achieved one through material selection. Natural materials with low embodied carbon generally are going to off gas less. They're going to have less harmful ingredients, and for that reason, they will aid in interior health. In addition, because these high performance buildings are continuously ventilated, as I showed you guys with our Brink system, these buildings also provide very high levels of indoor air quality because we're constantly exhausting old stale air and any contaminants or airborne dust or anything that might be floating around our space. And then we're also supplying fresh air, which we can filter and ensure that we have very high indoor air quality. These buildings are resilient because they manage water, as we mentioned. They also control air and vapor very effectively, and so they're built to last. This is big as the most sustainable building is an existing building. So we want to be building our structures to last for 100 years or more wherever possible. This one's a little bit maybe controversial, but we like to think that these buildings can be affordable, particularly air sealing, which, as I mentioned, has a very disproportionate effect, excuse me, on energy usage and comfort, can be added to most buildings without creating a significant impact on budget. And all these principles that I've mentioned can be applied to buildings of virtually any geometry, any design. So there's no reason why these buildings can't be beautiful. I think with sustainable buildings, sometimes we get caught in this trap of thinking that they have to be they have to appear a certain way, they can't be designed as flexibly. But in reality, the principles I'm going to talk about today are not limited by design, generally speaking. So there are a variety of different components that we use to achieve these qualities. We mentioned some of them already: air sealing, insulating, water control. The component that we're going to focus on primarily today and the impact that it has on high performance buildings is quality daylighting. So let's just define that term briefly. When we say quality daylighting, what do we mean? Well, I think this photo in particular does a nice job of summarizing some of the qualities that we consider to be provided by quality daylighting. We can see here two children sitting quite comfortably in a windowsill right up against the glass in their pajamas with no socks on. Despite the fact that the exterior temperatures are clearly quite cold and it's quite wintry and snowy outside, we can see that there's very little draftiness or heat transfer occurring through the window and wall assembly, as indicated by the lack of extra clothing required for these children. We can also see that they're reading their books via the natural illumination. So we are providing light here as well, which is a nice benefit, both in terms of improving interior aesthetics and also in terms of improving interior comfort. So just to kind of put some of these qualities into definition. Quality daylighting at 475 means that first we have a balanced window to wall ratio. Anytime we have a penetration in our enclosure, whether that's in our roof for a skylight or in our wall for a window or door, we are inherently creating a thermal weakness in that enclosure, and we're also creating an opportunity for air leakage to occur. So we want to be very considerate of how we're detailing our windows. Um, uh, we want to be minimizing the overall glazed surface area of the building while still providing the natural light and heat that these windows provide in order to minimize the impact on our overall heating demands. In addition, we want to optimize illumination or light that we receive through our fenestration via our quality daylighting to offset our electrical demands, while at the same time optimizing the solar radiation that comes with that light, the heat, to offset our heating demands. We want to have fenestration solutions, daylighting solutions that are thermally continuous, meaning continuously insulated with minimal thermal bridges and airtight. That'll help aid the overall performance of our enclosure. And then we want to provide for diffusion of natural light or shading to reduce visual and physical discomfort, particularly during cooling season. So now that we've defined quality daylighting, I want to turn your attention to this beautiful image. Looks to be a commercial space with a very large sloped glazing element on the roof here. And start the presentation with a very simple question. Based on the characteristics that I just defined, does this seem like an example of quality daylighting? See, we have an answer here in the chat. Mick said no. Thanks, Mick. Why would you say that it's not an effective example of quality daylighting? Well, I would say that this is not an effective example of quality daylighting for a few reasons. We said that one of the primary considerations that we want to take in mind when we are designing for daylighting is the window to wall ratio. In this case, we can see that the enclosure has been opened up significantly to utilize this sloped skylight throughout a significant portion of the overall enclosure surface area. And for that reason, we know inherently that the thermal performance of this enclosure is going to be compromised because the skylight is definitely not going to be able to provide as low of a U value or as high of an R value as a surrounding opaque structure. No worries, Mick. Thanks anyway. Um, Despite the fact that we've opened up so much of our enclosure for this skylight, we can see that it's not necessarily providing adequate illumination to offset the requirement for electrical lighting in the commercial spaces beneath the skylight. So we've compromised the thermal performance of our enclosure, and we're not really getting the benefits of that penetration that we were seeking. So no, probably not a great example of quality daylighting based on the definition of quality daylighting that we just made and based on this specific photograph. So what are some of the benefits of daylighting? Well, improved health and productivity is certainly one. When we have access to natural light in our day-to-day, in our office spaces, we are going to feel better physically. Natural light reinforces our circadian rhythm, which helps us to feel energized during the day and to sleep better at night. Students with access to natural light during exams tend to perform better, are shown to be more attentive. Even shoppers in retail locations with natural light tend to spend more time in store and spend more money on product. This is one, because the natural light provides a more pleasant shopping experience, and two, because natural light allows for the full spectrum of visible light to be perceived. So it allows shoppers to more accurately visualize the colors that are being represented to them in the products that they use. This full spectrum of light that natural light offers is also a great design tool. Natural light allows us to capture very specific qualities of light in order to create specific aesthetics. So there are definitely architectural benefits to utilizing daylight as well. Here in the image on the right, we can see the Kimball Art Museum by Louis Kahn, which features a long, narrow skylight at the ridge of this barrel roof. We can see that this skylight is deflected as the light enters to the interior. It's reflected back at the ceiling, allowing the space to be illuminated naturally without having UV come directly into contact with the art below. Again, a very specific quality of light and one that was obviously very thoughtfully considered for this space. Another benefit of daylighting that maybe we don't consider as frequently is the energy savings that daylighting can create. Basically, heat transfer occurs in our buildings in three different ways: by conduction, i.e., air transfer. I'm sorry, by convection, i.e., air transfer, conduction, which is heat transfer through a material, and radiation, which is heat from the sun that we receive via natural light. So, with fenestration, we want to be thinking about particularly our heating season, since we are, for the most part, in a heating dominated climate here in Brooklyn. And I know at least partially in the Bay Area, depending on how far inland you go. So heating and heating dominated climates, we're using most of our operational energy throughout the year to generate mechanical heating. And we can actually offset this mechanical heating requirement by providing natural light and the heat and the radiation that comes with it. However, we want to also be ensure that the elements such as windows, doors, and skylights that are allowing us to capture this radiation are not allowing for more heat to escape via convection and conduction than they are receiving via radiation. When we do get to a point where we have a high performance skylight solution or window, we can be relatively certain that we're minimizing air transfer or convection. We're minimizing heat transfer through the skylight assembly, i.e. conduction, and we're still receiving significant amount of radiation through the glaze surface. And we could actually get to a point where we're receiving more heat via radiation than we're losing via convection and conduction, which will allow our skylights to have a net positive impact on our overall heating demand. And I'll get into this in a little more detail towards the end of the presentation with an energy balance exercise. So why roof daylighting specifically? Well, roof daylighting, because of its orientation to the open sky and to the sun, is ideally positioned to capitalize on some of the benefits I already discussed: improved health and productivity, aesthetic and architectural benefits, and energy savings via reduced electrical loads and solar gains. Skylights are also ideally positioned to take advantage of the benefits of natural ventilation. I'll talk about this a little bit later in the presentation, but skylights, when opened, can capitalize on the benefits of natural ventilation via the stack effect, and can also allow for uh, ventilation during shoulder seasons, which can minimize our heating and cooling requirements. Skylights also, as we saw earlier, allow for exterior access, which is particularly relevant in urban environments where we might be limited in terms of how much private space we have outdoors. Skylights open up access to roof decks and green roofs, which is just another space that might otherwise be difficult to access. So looking a little bit closer at this relationship between skylights and windows, we know about windows that they mostly provide indirect daylight throughout the day and throughout the year due to their orientation. Because skylights face the open sky and receive so much more direct light daylight, they can easily be 3 to 10 times smaller than windows while still providing similar amounts of light. So if we look at this image on the right, we can see illumination measured in foot candles during a variety of different weather conditions. In the top, we have a direct sunny, not cloudy day, and we can see that illumination is measured at between 5,000 to 10,000 foot candles from the sky. As we have cloudier conditions, such as during a thunderstorm or where the sky is heavily clouded, we can see that illumination is reduced to around 1,000 foot candles. However, when we consider the fact that office work typically requires between 30 and 100 foot candles to complete comfortably, we can assume that the skylight exposed to the dark, heavily clouded sky will still provide illumination that will help us to significantly offset our reliance on electrical illumination. Again, looking at this relationship between skylights and windows, in the image on the right, we have three different lighting conditions for the same, we'll say, office space. In the image on the top, we can see that the window is on one exterior wall. We can see that the light is penetrating into the space partially, but that the space generally is not continuously or not evenly illuminated. So while some tenants might have access to this nice natural light, others will be kind of left in the dark, so to speak. What we can generally assume as a rule of thumb is that light will penetrate through a window about 2 times the head height of that window. If we add a clear story or a light shelf to that window, as we can see in the middle image on the right, we can increase the penetration of light to about 2.5 times the head height of the window. But it's only with skylights, as shown in the bottom image, where we can evenly illuminate a space, even for parts of the space that might not be directly adjacent to an exterior wall. So skylights do allow us to bring light into spaces that might otherwise be easy to reach and allow us to achieve even distribution of natural light. However, skylights in particular come with a whole suite of problems, generally speaking. And when working with contractors, they're often quick to bring up some of these problems, and they're often reluctant to put a hole in their roof for a skylight because of these problems have occurred in the past. Some of the problems that we hear about most frequently are glare and summer overheating. Because skylights are oriented towards the sky and do receive so much direct daylight, they are particularly susceptible to over illumination, i.e., glare, or overheating, particularly in summer months when we're receiving more radiation than we would like, and we have to offset that radiation via mechanical cooling. In addition, skylights, because of their position on the roof, are particularly susceptible to winter heat losses. If we have a skylight solution that is not thermally broken or is not continuously insulated, we can see the heat that we generate in our interior space rise and come into contact with the interior surface of that skylight and then be transferred outward. And we'll have to make up for that lost heat via additional mechanical heating and additional energy. And then finally, skylights are also susceptible to condensation, again, particularly relevant in heating season or the winter months. Condensation typically occurs when we have very cold exterior temperatures and our skylight solutions are not thermally broken. We can see the interior surfaces of those skylight solutions become quite cold. And as our warm, moist air from the interior, which we're heating and which we are generating a lot of moisture into, particularly in the winter months when we're spending our time inside, cooking, cleaning, showering, breathing, that warm, moist air comes into contact with the cold interior surface of the skylight, and that moisture can actually condense and drip down to the space below. Commonly perceived as a leak, but more often we find due to skylights creating condensation due to their lack of thermal protection. So looking at some of these problems in practice, here we have an example of a space which was inhabited by this man, Nick Grant. He was feeling quite warm in his office despite the air temperature being around 23 degrees Celsius, which is about room temperature. It's a little warm, maybe around mid 70s, but relatively comfortable. However, Nick felt like there was a radiator on the space and he couldn't figure out why. So he took out a thermal imaging camera and he photographed some of the fenestration elements throughout the space. And what he realized with the thermal imaging camera is that while the air temperature was 23 degrees Celsius, the interior surface temperatures of the skylight on the left and the windows on the right was significantly higher at around 40 degrees Celsius, which is up around 90 or more degrees Fahrenheit. So what's happening here is that because the skylights are not continuously insulated, they're not thermally separate, is we have very warm exterior temperatures. We're probably also having a lot of exposure to sun, and the heat from the exterior is being transferred through the skylight or window assembly to the interior. And the interior surfaces of the skylight and the windows are becoming much warmer than the interior air temperature, and they're actually radiating that heat inward. So it feels like a radiator's on or there's some sort of mechanical source of heat, but in reality, it's just thermal asymmetry created by the lack of insulation in these skylight and windows. So looking a little bit closer at this phenomenon, here we have two conditions. Building on the left, which you can see has less insulation, we'll assume that the window is double glazed and not thermally broken. And the interior air temperature in this case is pretty comfortable, again, 68 degrees Fahrenheit, while the exterior air temperature is much colder at about 6 degrees Fahrenheit. So what can happen under these conditions is that because our window is not thermally broken, the interior surfaces of that window can become quite cold despite the interior air temperature being relatively warm. And when we have this big gap in temperature between the air temperature and the surface temperature, what we can see occur is that our warm interior heated air will come into contact with the cold interior surface of the window. It'll cool and it'll sink, and then more warm air will rush in behind it, the vacuum that it creates. And that phenomenon of cold air circulating will create a feeling of draftiness, which is not due to an air leak, but actually just due to a lack of insulation. In the image on the right, we can see we add additional insulation to our structure. We improve our window from double to triple layer glazing. And despite the fact that the exterior temperatures remain at 6 degrees, the interior surface of our window is much warmer and much closer to our interior air temperature. For this reason, we eliminate that convective looping, which I described, and we're able to create a much more comfortable interior environment. If you live in an old, maybe mid-century multifamily building, you may notice that radiators are commonly located underneath windows. This is generally due to the phenomenon which we described here. The radiator is actually intended to warm that interior surface of the window and minimize the effects of thermal asymmetry. So in addition to even temperature distribution, we also want to ensure for even light distribution. This would be the most effective way to reduce our reliance on electrical illumination. And it'll also aid in visual comfort, particularly for tenants that might be visually impaired or hard of sight. So now that we've defined some of these comfort drivers, another fun photo exercise for you guys here. Um, Based on some of the problems with daylighting that we see occurring most frequently, what do you guys notice happening in this image? Let's answer in the chat. Thank you, Mick. It looks like the shades are pulled, is what Nick mentioned in the chat. Yes, that's exactly what we are looking to emphasize here. So we can see in this structure, the enclosure is almost entirely glass. We have a curtain wall pretty much throughout for all walls. So we know the thermal performance of this enclosure has been significantly compromised and that we're having to generate a lot of mechanical heating and cooling to compensate for the lack of insulation and probably air control at the enclosure. Yet despite the fact that the enclosure has been compromised in order to probably allow for extensive views for the tenants that are inhabiting the space. We can see that many of the tenants have chosen to reject these views, drawing their blinds probably to reduce visual and physical discomfort. So a simple improvement here would be to break up the curtain wall, the floor, and the ceiling of each story, which would significantly improve the overall thermal performance of the enclosure, while not necessarily compromising the quality of the view. So now that we've kind of gone over some basics about daylighting, about high performance, some things that we consider important, I want to get into some considerations for utilizing roof daylighting better in high performance buildings, starting with design considerations and then going into product considerations. Before I get into our design considerations, are there any questions? If not, I'll keep going here. Feel free to interrupt or drop a question in the chat at any point. So let's talk about some design considerations that we can keep in mind to utilize roof daylighting more effectively, particularly in high performance buildings. The first design consideration that I want to talk about is detailing. Skylights, windows, doors are unique in that they're really the only element in our enclosure that is going to be providing all four control layers. So when we look at this breakdown of a wall that we see on the right, this is actually defined as the perfect wall, concept coined by Joe Strubrick of Building Science Corp, that consists of three main elements: exterior cladding, control layers, and structure. Control layers can be further broken down into the four control layers you see here on the left, which in order of importance are water control, air control, vapor control, and thermal control. Skylights, windows, doors, as I mentioned, are unique and they're really the only components in our enclosure that are going to be providing for all four of these control layers. And for that reason, as designers, we need to be really considerate of how we're detailing the connections of these control layers from our enclosure to our fenestration. So when we are detailing the control layers, we want to be considering first how we're going to connect our water control at the roof to our watertight skylight assembly. So here we can see a skylight assembly features a thermally broken. We can see this frame thermally broken via its insulation. We can see it's triple glazed. So we can be fairly confident that this skylight assembly is thermally continuous. We are assuming when we purchase a skylight that it's watertight. This skylight is also, it looks like it's mounted on this curb, also insulated. So we want to be connecting the water control in our roof to this watertight assembly. This curb makes it quite simple as we can run the roofing membrane from the roof up the side of the curb and attach it to the skylight assembly, ensuring that we have continuous water control over that penetration. Air control in this case, we're detailing our air control at the interior. Again, we're assuming here that our skylight assembly is airtight, and so that all we need to do is detail the connection of our air control layer in the enclosure to the airtight skylight. In this case, we see this red membrane, which is an Intello Plus membrane that we looked at earlier, or something similar, which runs behind our trim up the light well, and then connects to the bottom of our skylight via some adhesive or tape. Vapor control, we don't really need to worry about as there's not really vapor moving through our fenestration assemblies, but thermal control is definitely critical. So we want to ensure that we have a thermal control layer in our roof, which is aligned with the thermal control layer in our skylight. In this case, we can see that we have exterior insulation on this flat roof assembly. We have an insulated curb as part of the skylight assembly. And so all we really need to do is ensure that our roof insulation is aligned continuously with this insulated curb. And if the skylight is thermally continuous, that'll ensure that we're allowing for continuous thermal control over this penetration. So when it comes to thermal control, placement is really important. Here we're looking at a window, but the same concept would apply to skylights. For this example, we're going to assume that we're looking at the same wall assembly in each of these three images. And we're going to assume that the insulation layer or the thermal control in this wall assembly is centered in the assembly. So what we want to do ideally is we want to align the thermal control layer in our window, which is the window assembly itself, in the case that product is thermally continuous, with the thermal control in our wall. And we can see here in the middle image that that is the case. And what we can see in these images is that they are each a thermal model. So they're representing different temperature strata using different colors, cooler exterior temperatures in blue and green, and then warmer interior temperatures in red and orange. In this middle example, which is our just right example, we can see that the red is continuous at the interior and the blue is continuous at the exterior. There's not really any blending of colors or kinking of colors, and the colors aren't really moving through the assembly or the window, which would be an indication that heat transfer is occurring. So we can be relatively sure here that thermal control was detailed effectively and that we have continuous thermal control over this penetration. In the image on the left, we can see that we are experiencing some thermal bridging as we moved our window out of alignment with our thermal control layer in the wall. And so we will experience some heat transfer around the window between the insulation in the wall and the window itself. And so you can see that there is some cooler temperatures at the interior corners of the window where some of our heat is being lost. The image on the right shows a similar concept. Now we've moved the window to the interior of the enclosure. Once again, it's out of alignment with our insulation layer, and we can see that some heat transfer is again occurring between that insulation layer in the wall and the window itself, indicated by some of these warmer interior temperatures coming dangerously close to the exterior of the assembly. The same concept would apply to skylights. We want to, again, ensure that the insulation in our roof, the thermal control in our roof is aligned with the thermal control in our skylight. Here we can see a skylight assembly similar to what we looked at earlier, triple layer glazing and a thermally broken frame. We can see that for the most part, there's not any thermal bridging occurring, perhaps a small thermal bridge here at the corner where we've kind of see some cooler temperatures. But from the roof to the skylight assembly, we can see that the exterior insulation in our roof assembly is aligned with the insulated curb. And for that reason, we have very nice isotherms running continuously from roof to skylight. So the simplest way to ensure that we are detailing effective thermal control from roof to skylight is to utilize the thermally continuous solution. And once we have done so, all we need to do is align the skylight with the thermal control layer in our roof structure. Many skylights aren't going to be supplied with an insulated curb as part of their assembly, as we looked at in these last few examples, but the same concept can be used for skylights built on a site-built curb. In this case, we can see the site-built curb consists of a stud cavity continuously insulated, and again, we have a thermally continuous skylight solution, and so very little heat transfer occurring um, in the roof or in the curb, and because the insulation in the curb is aligned with the insulation in the skylight frame, there's again very little heat transfer occurring at that joint. So this again is a well-detailed solution, something we would consider high performance. Moving into our second design consideration, which is daylight modeling. There are a couple different ways that we can model illumination throughout a space. The two examples that I'm going to give are also useful for achieving LEED accreditation for natural illumination and offset of electrical demands. The first tool that we have at our disposal is spatial daylight autonomy. So spatial daylight autonomy is a spatial modeling tool that can be used to demonstrate how much natural light is being received throughout the floor area of a building. So we here can see in these four images that there is light distribution indicated by different colors. So the amount of hours throughout the year that that space is receiving natural light are going to be indicated by some of these different colors that you see. For spatial daylight autonomy, we're trying to provide adequate illumination for as much of the space as possible. In order to achieve LEED credits versus via spatial daylight autonomy, we want to get a satisfactory result. Satisfactory meaning that at least 55% of the space is receiving at least 300 lux of illumination of daylight for at least 50% of the operating hours each year. However, we also want to ensure that while we are providing adequate illumination, we're not over illuminating. We want to minimize those issues with glare and overheating that we mentioned. So the other tool we have is annual sunlight exposure. Again, annual sunlight exposure can also be used to achieve LEED credits. And here we are also measuring the amount of light received throughout the floor area of a space throughout the year. But here we're looking to eliminate problem spots where too much light might be occurring. So an adequate result or a satisfactory result for annual sunlight exposure would be that we want to have no more than 10% of the floor area in a space receiving more than 1,000 lux of illumination for more than 250 hours each year. A very simple design consideration, but one that's a huge impact on how much light and how much heat we receive from particularly our roof daylighting elements is orientation. We know we're in the northern hemisphere. The sun is in the southern horizon throughout the year. It's higher in the summer and lower in the winter. So we can use these patterns as well as any site-specific conditions, such as neighboring buildings or trees, to ensure that we are uh, locating our skylights appropriately, and that we're also selecting the right glass type for the right locations to minimize heat gain or to maximize heat gain, depending on how much direct daylight we're expecting to receive throughout the year. Spacing, another critical design consideration, both in terms of limiting our window to wall ratio, but also in terms of providing even illumination and minimizing potential visual discomfort or our reliance on electrical illumination. As a general rule of thumb, or sort of a starting point for designing with skylights, we want to be thinking about spacing our skylights about 1 to 1.5 times the ceiling height of the skylight, center to center in both directions. However, this obviously will vary significantly based on a variety of different factors. One, the skylight type, specifically the glass type, and how much light that skylight lets in. The depth of the light well or curb and its splay will affect how that natural light is reflected into the interior and how deep it'll penetrate. And then also any furniture, shelves, interior partition walls, obstructions, any element that might reflect or block light should also be considered when spacing skylights. So now that we've talked a little bit about design considerations, I want to cover a few product considerations, things we can be thinking about when selecting skylight products. And then I'll wrap up with a quick energy balance exercise and get you guys out of here. So the first product consideration I want to bring up is thermal values. We've talked a lot about thermal continuity and about continuous insulation. Generally speaking, the thermal performance of a window or a skylight is measured by its U value being the inverse of the R value. So a lower U value means better thermal performance. The U value for a window consists of not only the U value for its glass, but also the U value for its frame and the psi value of its spacer. Because uh, heat transfer can occur between the glazing and the frame itself. The spacer, which is the element that runs around the perimeter of the window between the glass panes, is critical to ensure that we are minimizing heat transfer at that joint. So we want to be choosing fenestration that has what we call warm edge spacer, which is a spacer made from a non-conductive material. And because that element is linear in terms of how it transfers heat, we don't use U value, which is a measure of thermal transfer based on surface area or based in two dimensions. So the U value for a window or a skylight is going to be the weighted average of the U value for its glass, its frame, and the psi value of its spacer. Generally speaking, the U value of the glass is always going to be lower than the U value for the frame. So larger windows with more glass surface relative to the frame surface are going to generally perform better than several small windows where the frame represents a more significant portion of the overall window assembly. So what does this look like in terms of skylights? Well, a thermally continuous skylight or a skylight with an exceptional U value would probably look something like this. Here we can see triple layer insulated glazing, going to provide excellent UG values. We can see a warm edge spacer. So again, minimizing heat transfer between the glass and the frame. The frame, which is continuously insulated, we can see there's nothing penetrating this insulation. So we can assume that we're minimizing heat transfer through the frame. And then the skylight is also mounted on an insulated curb, which as we saw earlier, makes it really easy to detail thermal control with the surrounding roof structure. What would a skylight that's not thermally continuous look like? Well, it might look something like this. Again, we're looking here at a thermal model of a skylight assembly. In this case, we can see that our interior surface temperatures are not staying quite as warm as we might like. We're not seeing much of that red or orange, particularly at this joint between the skylight and the curb. We can see that there's significant blending of colors or kinking of colors, an indication that there is a significant thermal bridge and a significant amount of heat transfer occurring at that point. When we do have thermal bridging, such as what we see here, that's when we are at risk of condensation. So in the winter months, when that heat transfer occurs outward, the interior surfaces of the skylight will become quite cold. And as we generate moisture at the interior, and that moisture comes into contact with the cold surface of the skylight, we can see water form. So in addition to thermal values, we also need to be considering our spectral values for skylights, which are the values of the glass or the way that it portrays or allows visible light and heat. Visual transmittance is one spectral value, which measures visible light or the amount of illumination we receive through a glazed surface. And then we have solar heat gain coefficient, which is measuring the amount of radiation or solar heat that we're receiving to that glazed surface. Generally speaking, we want to be aiming for a ratio between visual transmittance and solar heat gain of around 2. That'll be an indication that there's a low E coating used in that glass, which is going to allow us to maintain our visual transmittance while reducing our solar heat gain. Where the ideal combination of visual transmittance and solar heat gain in a heating dominated climate has us optimizing diffused daylight. So we want to be using glass that has a high visual transmittance and solar heat gain so that we can offset our heating demand in the winter. But then we want to combine that highly transparent glazing with orientation as well as shading solutions so we can block that light and heat when we don't want it. So just looking at that ratio that I mentioned a little bit closer, here we have 3 different glass types. Image on the left shows clear double glazing with no coating. And we can see that this glass is allowing light and heat to enter at roughly the same clip. So the visual transmittance in this case is around 80%. Solar heat gain is around 70%. So our ratio is pretty close to 1. Similarly, if we add a tint to the glass, such as what you have on your sunglasses, we are blocking heat, but we're also blocking light. And so our ratio between visual transmittance and solar heat gain remains pretty close to 1. When we utilize a low solar gain, low E coated double glazing, as we see on the image on the right, we're able to maintain a high level of visual transmittance, but reduce our solar heat gain, creating sort of the just right condition that we discussed, that ratio closer to 2. Some final design considerations. One, ventilation. As I mentioned, skylights are ideally positioned to capitalize on the benefits of natural ventilation. One, be a nighttime flushing, particularly relevant in shoulder seasons when we have cooler temperatures at night than the much warmer temperatures we're experiencing during the day. During the day, in the shoulder seasons, we have illumination shining, light shining through our skylights. All the materials, all the fixtures in our office or our home are going to absorb that light and that heat. And then at nighttime, they're going to release it back into the air. They're going to release that heat back outward. During that period at nighttime, we can actually open skylights to allow that heat that's being released that was absorbed during the day to ventilate to the exterior. And then when we come in the morning, we can minimize the impact on our heating and cooling systems needed to offset that heat. In addition, skylights are ideally positioned to capitalize on the benefits of the stack effect, the tendency of heat to rise in our buildings and escape through penetrations. The stack effect occurs particularly in taller buildings where heat gets pulled to upper stories and then escapes through air leaks. As that air is moving upward, it creates a vacuum on the lower stories. And so as we're entering or exiting that building, more air is being pulled in from the exterior. However, when we allow this stack effect to occur naturally by opening our skylights and allowing this air to move through, we can actually experience some of the benefits of that natural ventilation, which could be used particularly in the cooling season to offset cooling demand. Final product consideration is shading or diffusion. Ideally, wherever possible in a high performance building, we want to be utilizing exterior shading. Motorized solutions where possible. Exterior shading is going to block heat before it ever has a chance to enter our interior space. So we won't have to generate any mechanical cooling to offset the effects of that heat. Interior shades, definitely better than no shades, but generally speaking, they're only going to block heat once it's already entered the space. So once it dissipates out from behind the shade and spreads throughout the interior, we will have to offset it with mechanical cooling. Here we can see fritted glass, which features a printed or digitally or ceramic frit, which is going to block glass consistently throughout the year based on the size and pattern that is selected. So a few minutes left here. I'm just going to wrap up with this energy balance exercise and I'll let you guys get on your way. So for this example, we're going to be looking at the energy balance in this beautiful rectangular prism of a building, masterfully created in MS Paint. For this exercise, we're going to assume that our building footprint is 200 foot by 200 foot. It features 36 skylights here shown at the roof, each 38 inch by 38 inch. And we're going to see, so that represents a total glass area about 323 square feet, or less than 1% of the overall building envelope. So in this exercise, we're going to see what the effects of these skylights are on the overall heating demand and then cooling demand of the building. As we were mentioned in the beginning of the presentation, heat transfer occurs through skylights in three ways. It occurs via convection or air transfer if our skylight is not airtight. It occurs via conduction or heat transfer through material if our skylight is not well insulated. And it occurs through radiation, which is light captured from the sun through the glazing surface. So radiation is going to provide heat. Convection and conduction are going to allow heat to escape in the heating season or to enter in the cooling season. So I'm going to flip to this next slide, show you guys a quick chart. Here we can see heat losses and solar gains through our skylights based on different skylight assemblies. So in the bars on the left, the column on the left, we have what we would consider a low performing skylight. And as we move to the right, we're improving the skylight using some of the characteristics that we defined earlier in the presentation. So we'll start with this double pane skylight on the left, which we can see is not thermal bridge free. It does not have an insulated curb. It has a relatively high UG value. And so we know that our heat losses are going to be significant during heating season because we're going to be losing heat outward via conduction because we're not thermally continuous. We are still getting some solar gains through the glazed surface, which will offset our losses, but they're not significant enough to offset them completely. As we improve the performance of our skylight, moving to a triple pane solution with a conventional spacer, and then a triple pane solution with a warm edge spacer, we can see that we're actually able to reduce our heat losses via conduction, thanks to that insulation and that improved glazing. And eventually, when we have what we consider an advanced component or a high performance component, we can reduce our heating losses to a point where we can actually offset them with the solar gains, the gains that we're receiving from the sun. Furthermore, if we go from this thermally continuous assembly and then add a higher solar heat gain coefficient glazing, we can actually increase our solar gains and get to a situation where we're providing more heat via radiation than we're losing via conduction. This is what we would consider, or what we call free heat in the passive house world, as we're able to actually offset our mechanical heating requirements using this heat from our skylights. So this table represents the same data that I described previously on the chart on the last slide. So again, from top to bottom, each skylight assembly we looked at with varying characteristics. What we can see is that in the topmost column, which I have boxed here for you guys, our double pane skylight that's not thermal bridge free with a relatively high U glass value, our heat losses are greater than our solar gains, and so we have a net negative impact on our heating demand. We remember from the earlier slide that the skylights represent less than 1% of our overall building enclosure, but we can see that in this case, they are representing 7% spike in heating demand, so not great. As we improve the thermal performance of our skylight, we reduce the heat losses while maintaining the solar gains. and we can actually get to a point where the heat losses are offset by the solar gains, and then the skylights have a net neutral effect on the overall heating demand. We then raise the solar heat gain coefficient to 50% in these bottom two rows, and we can see that we're actually able to get to a point where our heating demand, our solar gains are greater than our losses, and we actually have a net positive effect on our heating demand. So I'm out of time here, guys. Just going to skip these last two slides and get you to the summary. Um, but thanks for taking the time again to join me for this presentation. I hope that you found it interesting. Be happy to talk to you more about any of these concepts or products if they're interesting to you. I'll leave you with my contact information. And thanks again, Mike. Appreciate you helping me get set up here.
Appreciate it, Jeremy. Thank you so much. And if you have any questions in the room about your credits and so forth, Jeremy provided the form. Also, you can reach out to Sydney in regard to getting those units for this session added to your record. Thanks again, Jeremy, and 475. We'll see everybody at the next one.